Byzantine Fault Tolerance, often abbreviated as BFT, is a critical concept in distributed systems that addresses how networks can continue to function correctly even when some participants are acting maliciously or behaving unpredictably. In this video, we'll explore what Byzantine faults are, why they matter, and how systems can tolerate bad actors while still reaching consensus. A Byzantine fault is a condition where components in a distributed system fail in arbitrary and unpredictable ways. Unlike simple crash failures where a node just stops working, Byzantine faults are much more complex. A faulty node might send conflicting information to different parts of the system, deliberately lie about its state, or behave in any other malicious or random manner. This makes Byzantine faults particularly challenging, because you cannot predict what the faulty node will do next. The concept gets its name from the Byzantine Generals Problem, a classic analogy in computer science. Imagine multiple generals surrounding a city trying to coordinate an attack. They communicate through messengers, but some generals might be traitors who send false messages. The challenge is, how can the loyal generals reach consensus on whether to attack or retreat despite the presence of traitors? This allegory perfectly captures the challenge distributed systems face when some nodes cannot be trusted. To understand Byzantine faults better, let's compare them with simpler failures. Crash failures occur when a node stops functioning completely and doesn't return any result. This is relatively straightforward to handle. Byzantine failures, on the other hand, are far more problematic because the node continues to operate but behaves arbitrarily or maliciously. It might send different messages to different nodes, return incorrect data, or act unpredictably. This makes Byzantine failures much harder to detect and tolerate. There's a mathematical foundation to Byzantine fault tolerance. To tolerate faulty nodes, a system needs a minimum number of total nodes. The formula is n is greater than or equal to 3f plus 1, where n represents the total number of nodes in the system, and f represents the maximum number of faulty nodes the system can tolerate. This means you need at least 3 times the number of faulty nodes, plus 1 additional node, to achieve consensus. This ratio ensures that honest nodes always form a supermajority. Let's see how this formula works in practice. If you want to tolerate 1 faulty node, you need at least 4 total nodes in your system. To tolerate 2 faulty nodes, you need 7 total nodes. And to handle 3 faulty nodes, you need 10 total nodes. Notice the pattern. As you want to tolerate more faulty nodes, the total number of nodes required increases significantly. This is why Byzantine fault tolerance comes with a cost in terms of system resources and communication overhead. Byzantine fault tolerance relies on several key mechanisms. First, message redundancy. Nodes exchange multiple rounds of messages to cross-verify information. Second, voting and consensus. Nodes use majority agreement to determine the valid state of the system. Third, digital signatures. Cryptographic proof prevents message tampering and ensures authenticity. And fourth, state verification. Nodes cross-check information received from multiple sources before accepting it as truth. Together, these mechanisms enable the system to filter out false information and reach agreement despite malicious actors. One of the most influential BFT algorithms is Practical Byzantine Fault Tolerance, or PBFT, introduced in 1999. PBFT uses a 3-phase protocol: pre-prepare, prepare, and commit. In this protocol, one node acts as the primary and coordinates consensus, while other nodes act as replicas. Through these 3 phases of coordinated message passing, the system achieves consensus efficiently. PBFT was groundbreaking because it made Byzantine fault tolerance practical for real-world applications, dramatically improving performance compared to earlier theoretical solutions. Byzantine fault tolerance isn't just theoretical, it's used in critical real-world systems. In blockchain technology, platforms like Hyperledger Fabric and Tendermint use BFT consensus to secure distributed ledgers. In aviation, flight control systems employ BFT to ensure safety even if some components malfunction. In finance, distributed banking systems use BFT to maintain integrity and prevent unauthorized transactions. Any system where security, reliability, and trust are paramount benefits from Byzantine fault tolerance mechanisms. BFT enables trust in untrusted environments by providing a mathematical guarantee of correctness. By requiring 3 F+1 nodes to tolerate F-faulty nodes, systems can achieve consensus even when some participants act maliciously or unpredictably. This 2/3 supermajority requirement ensures that honest nodes can always outvote faulty ones. While BFT comes with overhead in terms of communication and computation, it provides the foundation for building secure, reliable distributed systems that can operate correctly in adversarial environments.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.